record it, go to a new tab. Okay, so we're going to talk about speed of a wave on a string. So you learned that the tension you guys hear that guy? He's so mad at FedEx. So the tension affects the speed of a wave on a string. And we saw if we have a bigger tension force, that resulted in a higher speed. Okay. We also saw from that lab that frequency will not affect the speed, wavelength will not affect the speed, amplitude does not affect the speed. And, you know, you can change the frequency and turn the wavelength changes and things like that. So we saw that. So far, the only thing we know that affects the speed of a wave on a string is tension. What else might affect the speed of a wave on a string? Any thoughts here? Type it in the chat box. I feel like this is a one-way conversation. I'm a little lonely. Any ideas on what might affect the speed? I'm waiting. I have no idea if anybody's typing anything. All right, I'm going to continue talking because I don't want to just sit here for half an hour. What it's connected to? Okay. All right. The medium. All right. Now we're getting somewhere. Okay. So I'll address what it's connected to. Really, if you have a string, and we're talking about a string right now, if you have a string that's that you're holding one end of it, I don't care what the other end is connected to. If there's tension in that string and you create a wave in that string, that wave is going to start traveling. It's not going to know what's on the other end until it gets there. Okay, so I would say what it's connected to is not going to affect the speed. Okay, now the medium, we're talking about a string. So the medium is the string. So what about a string could be changed that might affect the speed? Okay, how about the thickness of it or the mass of it? If you have a fatter, a more massive string, that's more inertia. It's going to be harder for that, that wave to travel through, I would think. That kind of makes sense in my mind. And when we're talking, sorry, I should backtrack. We're talking waves on strings. It could be just a string tied between 2 points. It could be a guitar string, a violin string, a piano string, musical instruments. You could tie a string to a tree and hold the other end and pluck that, and then the wave is going to travel down. So really any wave on a string. Okay, so I will say, the mass of the string will affect the speed. Okay, so we're going to get into a property called linear mass density. Okay, the symbol we use for that, yep, it's mu again, and that is just mass divided by length. Okay, so mass of a piece of string. All right, we need to work in kilograms. So if you're thinking string, you're thinking, well, that's a very small mass in kilograms. Yeah, it is. Okay, but we're working in base units here. L length of the string, and that'll be in meters. All right, and then mu is this linear mass density, and that'll be in kilograms per meter. Okay, so basically the mass per meter. You've got a heavier string, it's going to have more mass per meter. So that's a property of the string that we're going to be using here. Okay, so now the equation for speed of a wave on string is going to be given by this. And if you read section 3, you already know this. Okay, I want to be more clear here. That whole thing is under the square root Okay, so the speed is given by the square root of the tension divided by that linear mass density. Ft. Tension, of course, is in newtons. Mu, I just defined it above. I'm not going to rewrite that. And then V, of course, is the speed. And that is meters per second. Okay. All right, so that's really the equation here that we're going to be using. Whoops, I went through the V there. Let's do just a quick example, and I think we're about done with this. Okay, so this is the example we high school physics teachers like to use. All right, so I'm going to have, we've seen things like this before. Okay, so here's a string, horizontal, and that goes over a pulley here, and then we have a mass hanging down. The mass is what's going to create the tension in the string. So let's just say this is 2 kilograms. All right, and let's say we have a piece of string. Length of string, let's make it 8 meters. And the mass of 8 meters of string, we're going to say 20 grams. Okay. We're good to go. Let's just solve for, we're going to pluck the string here. We're going to send a wave down. We'll talk about reflection tomorrow. You saw in the simulation how it reflects back and forth like that. That's what's going to happen. We'll talk about that tomorrow. Right now, let's just be concerned with the speed of the wave on this string. Okay, so to get the tension, we're going to go back to last semester. Yes. Quick free body diagram. So this will be mg, which 2 times 10 newtons per kilogram, so 20 newtons. 20 newtons. And then the tension here, well, if the mass is not accelerating up and down, net force is 0. So we know that tension must also be 20 newtons. Okay. And then the other component we need is mu, the linear mass density. So we've got mass per length. So in this case, our mass, we need to be in kilograms. So 0.02 kilograms per length. 8, oh shoot, I did not bring a calculator out here. All right, so interactive time. I assume at least one of you has a calculator. If you could help me out with this, I think I can get mu. So 2/8. Yeah. Oh, I was just gonna say that. Darn it, Matt, you beat me to it. 0.0025 kilograms per meter. Okay, now we have the tension and, whoops, the linear mass density. Very straightforward. Square root of tension over mu. So then speed, square root of 20 over 0.0025. Okay, who's got the speed now? Do you guys usually just see my forehead when I write like this? Just notice that. Speed, calculator. I could, 89.44. Okay, awesome. It's like we're back in class together. So 89.44 meters per second, and that is it. Okay. Yeah, one thing to be careful with is when you're getting the linear mass density of the string, make sure, oh, my internet is unstable. Okay, when you're getting the linear mass density of the string, make sure the mass and the length go together. Whatever length you have, you need the mass for that length. I'm going to try to keep it somewhat simple given our situation, so I'll try not to trip you up like that. But, you know, it's something to be aware of. Make sure they go together, okay? All right. Trying to think if there's anything else I need to address right now. I think that's it. Any questions about this or general questions about anything or concerns about anything? Everybody still doing okay out there? Is everybody okay? Go ahead and unmute yourself if you, can I unmute everybody? I just unmuted all. This will be awesome. What breed is your dog? Hey, Ozzy, come here. Come here. Oh, I can't see. Here, come over here. Ozzy, come here, come here. Wait, there, can you see him? There's his butt. I don't know if you saw him very well. He just walked away from. He's a mutt. He's got some black lab in him and some hound here. Oh, a physics question. Can you switch back to the formula screen? Okay. Is this what you're looking for, Nahida?
Yeah.
Yeah, okay. And like I said, I'll save this file and put it on Canvas as well, and the video will be on YouTube. You could watch it again because it was pretty exciting. Okay. All right, I think you're all unmuted. Do you have any questions? Anybody? You can type it, you can talk it.
Can you calculate speed using wavelength and period?
Yes. Okay. So I'm going to scroll down here to a new section. So if you remember in yesterday's video, which it looks like not everybody watched that. Don't hurt my feelings like that. Okay. So in yesterday's video, we had a wave like that. And we talked speed is distance over time. Okay. So the distance we have, for a wave, a distance that we can define is the wavelength. Okay. And then whenever you're calculating speed, you need the corresponding time for that distance. So if we're talking about the distance as one wavelength, we need the time for one wavelength, which is period. So there you go. I'm pretty sure the question was calculate speed with wavelength and period. That's it. Okay.
Oh, I see.
And then, you know, we also talked yesterday that frequency is 1 over period. So you could also say V equals frequency times wavelength. Okay.
And that's in seconds?
The period would be in seconds, yes.
Okay.
The frequency, so period is in seconds. Frequency is hertz, or really it's 1 over seconds. Cycles per second, waves per second, whatever it is. And then the speed would be in meters per second, because wavelength we're going to have in meters. Okay, anything else? Any other questions before we end this? All right, I'm hearing nothing. So we will go ahead and call this done. I know you were excited to see there's a Wiley Plus assignment. All right, it's only 2 problems, and it's dealing with this speed of a wave on a string. So this exact equation, in my opinion, they're pretty straightforward. I don't think I even picked any that gave you the mass and the length of the string. I think you're given the linear mass density right there. So be aware of that. You know, going back to our equation. Oh, why isn't my screen moving? Okay, here we go. If you're given linear mass density, don't go in and try to use this equation. You're already given what you need for this formula here. So be aware of that. Okay, are we good to go? I'll take that as yes. So, you know, work on that Wiley Plus, finish that FED assignment, get that submitted if you didn't do that already. Let me know if you're having any trouble with anything. If you're just having trouble completing the assignments on time, that's totally fine. Just keep me posted on that. So tomorrow we're going to do some wave reflection and interference. We might get into standing waves, but standing waves is kind of the bigger topic. So I might save that for next week. No school Friday. Spend some time with your family, because I'm sure you haven't spent enough time with them lately. And then Monday is it's a teacher workday, I guess. I forget what they call it. So so you basically have a 4-day weekend. So try to get caught up on some things if you're a little behind on the schoolwork. Again, please don't hesitate to send me any questions if you have any. All right. Okay, sounds like we're all good. Oops, what did I click here? Okay. Hey, there's Noah. All right. I didn't mean to do that. I don't know what I'm doing here. Okay, I'm going to try to, shoot. Okay, I'm going to stop